effort, the SUbsonic single aft engine, or SUsan. Enjoy the video.
Hi, my name is Ralph Jansen, co-principal investigator for the SUbsonic single aft engine activity under the Convergent Aeronautics Solutions Project, also known as SUsan. I'm pleased to introduce the SUsan aircraft concept, which is intended to reduce fuel burn, emissions, and the cost of air travel.
Since the dawn of flight over a century ago, aircraft design has evolved and adapted to meet the changing needs of the aviation industry. As we look toward the next generation of aircraft, we're faced with a greater challenge that requires a transformation in modern aviation. Since the introduction of the twin-engine jet nearly 5 decades ago, the aviation industry has yet to see a large single-engine certifiable aircraft design. With aviation currently contributing 2 to 3% of all carbon emissions, the push for sustainable air travel will impact all aspects of aircraft design, from the way energy is harnessed to the way power is generated for increased efficiency in flight. NASA is developing a subsonic regional transport aircraft concept called the Subsonic Single Aft Engine Electrofan Aircraft, also known as SUsan. This advanced hybrid electric aircraft concept uses a 20-megawatt electrified aircraft propulsion system to enable effective propulsion airframe integration. SUsan is specifically designed to minimize environmental impacts by using less energy while maintaining current speed, size, and range of large regional aircraft. Alternative fuels will be used to further reduce emissions. The goal with this aircraft is to introduce new technologies and design configurations to help reduce emissions by 50% within the next few decades and eventually achieve zero carbon emissions. Developed with practical constraints in mind, SUsan must operate using existing airport infrastructure, be flight certifiable, and cost-effective. Operating with a hybrid powertrain, the aircraft features a single aft turbofan engine which produces thrust and electrical power for a number of distributed wing-mounted electric engines. SUsan's design configuration and components enable advanced propulsion airframe integration for propulsive, thermal, and aerodynamic benefits that reduce energy usage, cost, and fuel burn. Trade studies are conducted across the aircraft, propulsion, power, and control systems using a combination of parametric and higher fidelity tools. Aerodynamics optimization using high-fidelity computational fluid dynamics, or CFD, simulations of the aircraft shape, combined with internal CFD to optimize the propulsors, is used to maximize aircraft and engine performance. SUsan's powertrain includes deep redundancy, with a single-use battery that can serve as a power source in the event of engine failure. The powertrain also features an advanced thermal management system built to optimize heat management of the battery, electrical system, and turbofan to ensure safe performance at high altitudes. Addressing a key challenge in electrified aircraft, NASA is maturing electrified aircraft propulsion technologies to maximize performance with minimal weight and improve thermal management of aircraft power systems. SUsan leverages other NASA research activities like the 1.4 megawatt high-efficiency megawatt motor, also known as HEM, the Heather power converter, advanced cable and circuit breaker technologies, and advanced thermal management systems. As we look to the future of aviation electrification, NASA's research in electrified aircraft propulsion technologies and aircraft concepts will offer new possibilities for introducing cleaner and more efficient aircraft across key markets, including on-demand mobility, short-haul regional air transport, regional jet, and single-aisle aircraft. Electrified aircraft propulsion has the potential to enable significantly different types of large transport aircraft. As we embark on this new journey, ongoing flight research will help inform future standards and aircraft certification processes. NASA's Aeronautics Research Mission Directorate has made a critical commitment to showcase practical vehicle-level integration of megawatt-class electrified aircraft propulsion systems to help demonstrate these technologies. This will require increased efforts and collaboration from industry partners to transition technology into commercial products and improve designs for implementation in larger transonic aircraft. Aviation has evolved from the piston engine age to the jet age and is now moving into the electric age. SUsan is a concept to introduce electric aviation for large, fast, long-range passenger planes.
We're seeking to identify airlines as well as large and small U.S. companies interested in partnering on the development of the SUsan concept. Near-term collaboration opportunities exist in the development of a 25% scale flight research vehicle for integrated flight, propulsion, and power control system testing. Through collaboration, we can help mature the full-scale aircraft concept and underlying technologies for introduction into the global fleet within the next few decades.
Welcome back. I would now like to welcome to the stage Ralph Jansen. Ralph is the principal investigator for SUsan. Ralph, welcome to Imagine Aviation.
Thanks, Steve. I'm happy to be speaking with you today.
Excellent. It's such an interesting video and such an interesting concept that you've been working on for a little while. Ralph, your approach to SUsan, it does seem novel in a few different ways compared to maybe traditional research. What stands out to you and your team on the different approach you were taking to research in this area?
Yeah, I guess there's a few things that I think are a little bit distinctive on SUsan compared to other electric and hybrid plane activities. I think there's a kind of wide-held conception that these sorts of planes depend on battery advances and also can never be something that goes for a long range or fast. So SUsan uses a bunch of different innovations. We're doing a trade study to figure out whether we can build a plane that flies fast with batteries that are achievable and some other very advanced power systems, but still is constrained to run inside airports that exist, so you don't have to run a massive new infrastructure. So I think what we're trying to do here is take some new ideas in electric planes and make them very practical for the biggest market sector, which is the single-aisle aircraft market, without reinventing the airport.
Yeah, a lot of technology today that I've seen is maybe not hitting that single aisle craft that as you said, and that your team knows well better than any of us, and that's where it goes. I mean, that's where the money is. That's where the thrust is for airline advancement and development. That's where people fly. So what made it your decision to address that market versus starting with smaller aircraft or going to anything UAV like?
Sure. There is a lot of innovative work going on. I think we're entering the third generation in air travel with electric being introduced. And there's a lot of innovation both in the private sector and the government sectors in these areas. Air taxis and smaller planes, for example, are an exciting area that both externally and with NASA we're moving forward. However, like I mentioned, people don't think it's not believable that they can do electric at single aisle size. So what are we trying to do here at NASA? We're trying to do the things other people think are impossible, and that's what CAS is for, right? So that's what SUsan's about. While we are moving, I mean, we have flying prototypes and one certifiable flying small airplane in electric. We have a whole different NASA project where we're building up the power technology to do megawatt class electric for sort of planes that are bigger. And then this is to figure out how we do full-blown electric on a single-aisle aircraft, hybrid electric specifically. I'll say a bunch of things about electric here. So I just wanted an example. When I talk about megawatt, for those that aren't electrical, that's about the power of 10 car engines. And that's the technology we're starting to take to aircraft level with a different project called the Electrified Powertrain Flight Demo. When I talk small planes, they may be in the tens of kilowatts. 10 kilowatts is like 10 hair or 5 hair dryers in your house. Is the size of motors of the 10 kilowatt motor. What we're talking about here is 20 megawatts worth of power. That's about enough power to run half of a suburb. And that's what a single aisle airplane uses in power. So we're trying to figure out what we can do that's an order of magnitude beyond the stuff we're doing on our other flight project.
It's interesting, and one of the components I've saw in the video, and I've read about your research. This isn't just technology development in a lab per se, and that's not really fair to say it like that. But it's almost seems like you're approaching a new way to approach flight experimentation. The flight experimentation approach really seems novel and interesting. Please say a little bit more about how you expect to change the way we think about learning through rapid, low-cost flight research.
Sure. On CAS, we try to do technology, but we're also trying to do innovative things at NASA, right? So one of the things I'm hoping to do with my co-PI here and the team is to kind of innovate a lot faster at NASA. And we're going to do that by concurrently doing learning through analysis and learning through experiment. And the way we do that is that we have enough resources on CAS to do studies of a 180 passenger vehicle. But we are concurrently doing the design of a 25% unpiloted prototype that would be very useful for integrated flight power and propulsion control research, and also at a much lower cost point, really forces people to work through interfaces that they would normally put off the details of for 10 or 15 years. So that's what we're trying to do. We'll see if it works. We don't currently have enough funding to complete a 25%er, but we are building parts of it that are critical right now.
Nice. That's great. There's a couple questions in the chat coming in that I'm sure you get a lot. So let's jump into them. Is how does Susan land if the single engine fails during flight?
Yeah, I maybe used the wrong naming nomenclature when I called it the single aft engine. When I think of an engine, I think of something that burns fuel. So it does have one fuel burning engine. But in the current configuration, we have 16 electric engines. The FAA is adopting the term electric engine for an electric propulsor. So really, this plane has 17 engines on it. And the rear engine is used in a atypical way. It produces a little bit of thrust, but it also runs 20 megawatts worth of generators so it can run the wing engines. So what happens when that engine fails? It goes to a battery backup, a single-use battery backup. Now, for most aircraft, assuming we get this thing built, for most aircraft, that battery will never be used because it only exists when the engine actually fails. But that's how we can back it up. So we're building in tremendous redundancy, and part of our thing is to look at the regulatory and certification barriers, because technology solutions are wonderful, but we also have to be able to certify. And so obviously this is not the same as two fuel burning engines. And so we need to explore and define a path for how you certify a big plane like this that has one thing that's a fuel powered generator and one that's a battery to fly.
Yeah, I would think that that's going to get quite a lot of attention with the certification folks. You mentioned earlier in your either in the video or in talks we've had before about the airport infrastructure for electric aircrafts. That would be a need for something like this. You mentioned that it's minimal impact though on the aircraft or the airport infrastructures for the Susan concept. But talk to us a little bit about what changes would need to occur. in the infrastructure of any of our airports for Susan to be scaled?
Yeah, so the way Susan's designed, it fits into the gates of a standard single aisle 118-foot wide thing. The typical thing you may need on a lot of electric planes is either an ability to charge them or to swap batteries. We don't have any of that for Susan. You put energy onto the plane with fuel. Why is there a benefit? Yeah, there's a two-part potential benefit here. The plane is just made more efficient by integrating this hybrid system. It's made more efficient propulsively, and the engine thermal efficiency is upped, and the ability to kind of arbitrarily place thrusters where you want them on the airframe gets you an aero benefit. That's what we believe. That's what we're trying to figure out in our study. So it's just a plane that uses less energy. The second part, which we haven't explored as much, is the fuel side of it. I mentioned that we will get a benefit on energy use, and we will get more of a benefit on emissions because we'll use alternative fuels. I'm asked frequently about, hey, is electric and things like sustainable aviation fuels, are those two counter technologies? My answer is no, they're not. They're definitely not on this thing, because we're designing it so you can run it on Jet A. But if we get sustainable aviation fuels into there, that is an additional emissions benefit. So in this configuration, those two are complementary technologies. And then we want to explore some stuff beyond the typical sustainable fuels solutions, but we haven't gotten into that very much yet.
Okay, yeah, and I assume that that's future work that would go on if everyone thinks that's an important addition to this. There are some questions in the chat that kind of relate to some of this. And it's asked if the gas engine fails, but if the engine that is on any type of fuel, gas or biofuels or anything, if that fails, what kind of range are you talking about with the backup batteries that you have to enable it to land safely in an airfield?
Yeah, that's a great question. So we're calling this a regional plane for a couple reasons, but one of them is because we're designing for a 30-minute flight on the battery. So you're not really going to do transoceanic on this unless you're hopping along a coast where you're still within landing space. But our size is 180 passenger, which is like a big single aisle. This serves really well to low-cost carriers. Like there's a couple big European ones and US ones. You could cover any domestic route and be safe, and it's not really intended for transatlantic operations.
That's great, and I love a lot of the cast efforts in this one in particular as well. It really just goes with the theme of that Catherine mentioned this morning of discomfort and making people uncomfortable with change and with dramatic change and with reaching. So, and you see it in a lot of the questions you must receive every day when you go out to industry, when you go out to regulators. You probably realize a lot of these. Lots of people are becoming uncomfortable with something like this. How has that discomfort impacted your approach to pursuing, Susan, the technologies and where you think it could go for civil aviation?
Well, any of these leading edge ideas always make people uncomfortable. So it's fully expected, right? And it really, the reaction, it depends on sort of the audience. If you're kind of talking to somebody who's coming recently out of college that sees the pace of innovation out of companies like SpaceX and others, and how we've gone from nothing to air taxis flying quickly, and we've gone through fully reusable, economically effective rockets. This doesn't seem very innovative to them. If you talk to other audiences, they think it's really leading edge. So I really think it's different depending on the perspective of the person you're talking to.
No, that's a great point. And I think that emphasizes the enthusiasm that we heard yesterday with the student panels. It's a great perspective that refreshes our industry, and it's really great to hear. Well, that's really all the time we have for questions and answers today, Ralph. I really want to thank Ralph Jansen for the video and the Q&A session regarding Susan. Thank you, Ralph, very much.
Appreciate the invite. Thank you.
Great. Now I want to introduce our final CAST presentation.